Hello, everybody. It's a pleasure to be here in this interesting conference. My name is Felipe Caballero Briones, and I came from Instituto Politécnico Nacional in Mexico. The presentation I am going to show you in this day is structure and chemical environment in cerium potassium titanates mixed with reduced graphene oxide composites and its relationship with photocatalytic hydrogen generation. Um, First, the photocatalytic activity is a well-known phenomenon. It requires a semiconductor that, upon illumination with light of the proper band, energy, it produces an electron-hole pair, and afterwards it produces an hydrogen or oxygen in the valence band and the conduction band that will lead to photo reduced or photooxidized pollutants or to hydrogen generation, which is the point of this presentation. Of course, the energy will depend on the solar spectrum of solar radiation, and for photocatalysis, it's interesting to engineer materials with band gap close to the sun maximum. For example, in the previous work we have produced, we have a composite made of molybdenum, titanium oxide, and reduced graphene oxide, and also another composite made of cerium oxide, cerium titanate, titanium oxide, and reduced graphene oxide that has this band diagram that is proposed to hydrogen production. So you can see here that the reduced graphene oxide is the skeleton that sustains all the photocatalysts, and upon illumination, the electrons and holes diffuse through this graded interface and produce hydrogen in the extremes. And reduced graphene oxide acts as a sensitizer that reduces the recombination of the electrons and then increases the rate of hydrogen produced. This is the presentation contents today. The background is already done. We are going to speak about the methodology, the results, and the conclusions we have. We prepare our materials by hydrothermal reaction. We mix all the components first, and then we use this setup to produce the materials. And in the first case, we have different materials prepared. We depart from titanium oxide, commercial titanium oxide, that is modified hydrothermally by adding potassium hydroxide, and then potassium titanates are produced. You can see here the Raman shift from the titanium oxide signal to lower Raman shift, that is higher energy, that indicate the production of introduction of potassium, and then this potassium is substituted by cerium, that is the sample CT. And here you can see the structural evolution from titanium oxide. Afterwards, when you produce potassium titanate, you can see here noble peaks upon the modification of the structure. And then after cerium is introduced, this peak arises that corresponds to cerium oxide. And after incorporating this material to reduced graphene oxide, you can still see here that the titanate peaks, and these are the bands of reduced graphene oxide. Corresponding to the structure, we depart also from titanium oxide. These peaks correspond to potassium titanium oxide, and to cerium oxide here. And after incorporation of the reduced graphene oxide, the structure remains the same, but the size reduces because the dispersion of the particles within the graphene matrix. These are the patterns RXT, that cerium oxide RXT, and after incorporation of cerium, you can see here the peak of cerium oxide that remains upon incorporation of reduced graphene oxide. This is the band gap. You can see here in the tau plots in the indirect band gap when titanium oxide has the known band gap of 3.2, 3.3 electron volts, that becomes reduced until 2.9 electron volts around after the incorporation of cerium. That this will be easier to get photocatalytic activity because the reduction of the energy of the band gap. Here in the XPS, you can see a mixture between cerium-4, that are these peaks, and cerium-3, that indicate the presence of oxygen vacancies that are fundamental to the photocatalytic activity, because the photocatalytic activity in this case will work through the oxygen vacancies, oxidizing and reducing the cerium moiety. And here finally you can see the photocatalytic activity, how the amount of hydrogen that it is produced during the time. This experiment is done under ultraviolet irradiation in a closed system, and hydrogen is detected by chromatography, by gas chromatography. Here you can see by the time there is an amount of hydrogen produced by titanium oxide and also by graphene oxide, and after potassium is incorporated, the amount of hydrogen increases dramatically, and upon incorporation of reduced graphene oxide, that is the black signal, you can see here a higher hydrogen production that is attributed to less recombination. We tried three different compositions of the materials, of the composites, with increasing amounts of cerium. And the increasing amount of the higher amount of cerium is this one, CTG3, CTG2, and CTG1, that is the less amount of cerium. And this is attributed to the deleterious effect of cerium oxide on the activity, the photocatalytic activity, because as much cerium oxide 4 is produced, it impedes the generation of hydrogen. Finally, we want to conclude telling that we have prepared the cerium, titanium, oxygen, reduced graphene oxide composites, prepared and tested for photocatalytic activity. These were prepared by sequential modification of titanium oxide to potassium titanate. Then this potassium is substituted by cerium, and cerium titanate is made. And finally, we intercalate this composite with reduced graphene oxide. The controlled incorporation of potassium was achieved, is followed by the substitution of cerium, and this was confirmed by Raman, XPS, and X-ray fluorescence spectroscopy. The sample CTG1, that is the one with less cerium amount in the composite, has a good distribution. It has the smaller band gap, which favors light absorption with less energy. And structural and morphological analysis indicates that graphene oxide acts as an efficient support for cerium titanate dispersion. The particles are better dispersed, so the photocatalytic activity is increased. And finally, sample CTG1 has the highest hydrogen evolution rate, with a 500 micromole per gram in 4 hours. That is a promising material for green hydrogen production. And finally, we would like to thank you all our team, and thank you for inviting us to this conference.